that, I'd like to invite our next speaker, Bhupen, who leads the Manufacturing Industry Futures team at Autodesk Research, has more than 2.5 decades of experience working in industry, is a fellow of the Royal Aeronautical Society, and on a personal front, he enjoys golf and also likes classic car restoration. So I'm guessing we're getting a team out here. Bhupen, over to you.
Thank you, Ajit, for the welcome introduction. It's a pleasure to be here and being able to present today as well. I'm just going to share my screen. I've got a rather convoluted setup here today, so I hope it works. I've got 2 PCs. Can you see my presentation?
Yes, it's coming fine.
Excellent. Okay, I'll begin then. Right, so what I want to do today is really talk about the convergence between design and make in additive manufacturing and what we're doing in Autodesk, specifically Autodesk Research. So, sorry, my PC is not advancing. Here we are. Okay, so I'm going to give you a brief overview of Autodesk, the solutions we have, and the concept of convergence. Then we'll look at how we're pushing the boundaries of generative design to the next level, and also closing the loop on additive manufacturing and digital twin and thread for DFAM. So really, a quick overview of Autodesk. Now, those who don't know Autodesk, but Autodesk is well known for innovative software solutions in many industries, which include architecture, engineering, construction industry, the media and entertainment industry, and design and manufacturing industry. And we help our customers who design and make everything from smart cars to skyscrapers, from bridges to blockbusters. Our tools automate things that are designed in the digital world and then ultimately made in the physical world. So, for those who may not be aware, Autodesk currently have 2 software offerings for design for additive manufacturing. The first one is Fusion 360. It's a cloud-based 3D modeling, CAD, CAM, CA, and PCB software platform for product design manufacturing. It can, with design and engineering products to ensure aesthetics, form, fit, and function, reduce the impact of design, engineering, and PCB changes to ensure manufacturability with simulation generation tools, and also directly edit existing features or model fixtures with the only truly integrated CAD and CAM software tool. The more professional tool for additive manufacturing is NetFab. It's a feature-rich software application, but it also has integration with Fusion 360 as well. And so it streamlines the workflow and automates the processes around 3D print preparation. It has build preparation, simulation, and slicing capabilities. And also, as I mentioned, has very good integration with the Fusion 360 suite, and so giving you an end-to-end capability there. So, convergence of design and make. Right, so convergence is essentially the coalescence of technologies and processes that migrate across various traditional boundaries, as we know them. So whether they be between industries, between physical and digital, or in our case, between design and manufacturing. And the way we work is changing faster than ever, certainly for our customers during the global pandemic. The pace of adaptation has accelerated greatly. Manufacturers are certainly under pressure to deliver better products faster, at low cost, and with less waste. So sustainability is very much an issue there as well. And to compete in the future, they'll need to connect their design and manufacturing processes so that all team members can collaborate seamlessly. And especially so when supply chains are becoming more and more complex and convoluted as well. So in our kind of vision, we have 3 components to achieve this. First is connect, automate, and network. So firstly, with connect, what we want to do is connect mechanical design to simulation, and we do that very well already within our software. And then to connect software with hardware. And in terms of automate, we're looking at automating the design to manufacturing process, and then automate manufacturing process with simulation as well. So this is the simulation for design for manufacturing as well. We want to also automate production with advanced manufacturing, so robotics, for example. And finally, network. We want to network the top floor, essentially the design floor, with the shop floor using a digital twin, and secondly, network with customers, the entire supply chain that they have using a cloud platform, cloud-based platform. So pushing generative design to the next level. So we have new capabilities that go beyond traditional solid lattices, and these are highly optimized hollow lattices for super lightweighting and enhanced stiffness. Using Autodesk Generative Design in Fusion 360, we came up with multiple design options and then selected the top choice for simulation testing. Now, in this case, our collaboration with Stuart Haas Racing and Renishaw, we used the 500Q quad laser powder bed metal printing system to manufacture the new brake pedal for load testing. And with the new brake pedal, Stuart Haas Racing realized a 32% reduction in weight and a 50% increase in stiffness with the optimized design coming out of Fusion 360. So with the technologies that we have, we are now pushing them to the limits of efficiency. However, whilst we design for additive manufacturing, they are not cognizant of the machine and the process that they are used, that are applied to manufacture the parts. Another project where we're actually pushing the limits of generative design is Project Monaco. So Project Monaco is a EU-funded project which is part of the Clean Sky 2 initiative, and it's focusing on the design and manufacture of large-scale additive manufacturing components. In this case, what you're seeing here is a turbine center frame. It's a hot component, and what you're seeing there is a airflow duct. Now, the design has been derived using multi-physics optimization and generative design, and novel workflows to reduce mass and pressure loss while maximizing stiffness as well. And the key achievements in this particular project are consolidation of the frame assembly, which is essentially 150 parts into one, assembly mass reduction of about 40%, and then pressure drop reduction more than half of the baseline design, which is across the three manifold inlet and three outlets as well. So a very, very highly efficient design, but then it has challenges in terms of manufacturing as well. So closing the loop on additive manufacturing. So why we need a closed loop control system? So as mentioned earlier, we talked about the convergence between design and manufacturing, where our strategy is to connect, automate, and network. In order to realize this, we have put a great deal of importance on connecting software to hardware. It is vital to be able to do this, since having real-time connection and process automation, we can significantly speed up the design and make process. So current techniques for simulation, whilst being reliable and robust, take too long and are pretty much offline. Having software connected to machines is the first essential step, and then enabling closed-loop feedback control will save time, costs, increase quality, and output. No doubt, it's not an easy task, but certainly that's the direction we should be going. A key ingredient in being able to do this effectively is to have the essential middleware that is able to connect software and hardware. So Autodesk Machine Control Framework is something that we are currently working on. And when you want to actually control the strategy for additive manufacturing control, this is a picture which I always like showing. It's by Blazier and al., which was published in 2015. But what it does do, it really just shows the connectivity between the in-process measurements and the post-process measurements with real-time parameter control strategy. Anyone who wants to have a read, and those who are familiar will agree with me. So Autodesk Machine Control Framework. So to this end, Autodesk have created an open source middleware called Autodesk Machine Control Framework. In the same way Android allows developers to connect with mobile phone hardware and its sensors, Autodesk Machine Control allows 3D printing community to develop their own control strategies for the additive manufacturing process of their choice. So whether it's laser powder bed fusion, or whether it's WAM or other DED processes, you can use this middleware. Now, Autodesk are doing this to democratize additive manufacturing technologies, to catalyze the AF market, and to help startups and hardware developers to accelerate development. In the very same way we did this for one of our popular DFAM tools called Mesh Mixer, which many of you may have used. So an example of closed-loop application stack. You start off with Fusion 360, where you have your CAD, data preparation, nesting, and support structure generation, and toolpath and process simulation. What happens there is that all the data gets transmitted to AMCF, where AMCF will be responsible for process control, build file management, hardware control, subsystem synchronization, and error handling. And then in turn, it controls the hardware. So in this case, working with ScanLabs, we have the ScanLab controller and PLC for real-time control of laser system and mechanical system. In turn, we also interface with ScanLab Open Interface extension to actually bring in all the sensor data. And all those measurements are then reported back to AMCF. And what it does, it actually does the data recording and also the process monitoring as well. And then it feeds it back to the design. And this is an iterative loop. And the benefit of this is real-time control. And it allows you to do feedback loops from the data you've gathered from the manufacturing process back into your design and simulation process. So I'll give you an example of how we've implemented this. In addition to working with ScanLabs, we're also working with Technical University of Ireland. So it's an overview of the strategic collaboration we have with them. We have created a truly open architecture, a closed-loop selective laser melting system. AMC is used to orchestrate the data acquisition, communication, and control between an array of sensors, PLCs, laser, and laser control devices, which ultimately connect to the software to ensure that your build is as close as possible. Sorry, your as-built is as close as possible to your as-designed. Other industrial collaborators here, we have EvoBeam, One Click Metal, Hamill, and also BNA Group. So implementation strategy for AMCF is really based on 3 pillars. So we have industry, where we really want to drive collaboration with machine manufacturers, enable SMBs to automate workflows using AMC. And the second pillar is academia, is to collaborate research with university research labs, and also use AMCF for educational use. Teach students how to connect software and hardware, so essential these days. And finally, research. We want to, within Autodesk as well, is to research new application cases for using Autodesk products, and also applications such as DED. We're currently working on WAM process to implement closed-loop feedback control. And what we want to do is, as we start developing new applications, we want to share the projects as open source as well. So anybody out there can take AMCF and replicate some of the applications that we have. And all in all, what we want to do is establish an AMC community and an ecosystem for this technology. So, well, you can download this. It's open source and available. So the GitHub repository there, you should be able to access, and I'll share this later in the chat screen. You should be able to download it, and it's got some really good examples and some help files for you to get started as well. And finally, digital twin and thread for additive manufacturing. Andrew touched on it previously, but I totally agree with him. And looking at the bigger picture, one of the key capabilities that Autodesk and my team are currently working on is to realize the creation of a life cycle digital twin and thread for the design make use process. So it's specifically focused on speeding up the product development cycle by connecting each of the disparate process or discrete digital twins, as we call it, connecting them together through a single effective data abstraction layer or a unified data management system, we call it UDMS, as well as developing and connecting discrete digital twins for conceptual design, engineering design simulation, manufacturing, inspection, assembly and test, and also operation and sustainability. And really, one of the key things with the digital twin is that you can use the data acquired to do various things. You could do analytics and also use them to loop back to the conceptual design, where you can actually improve your design on an iterative basis, going from one generation to another generation. So yeah, with that being said, that concludes my presentation. Thank you very much.
Thanks for the lovely talk, Bhupen. It was fairly clear that the future of AM computational tools is looking promising. What timelines do you see being put for the AMC that you showed to us? In terms of what do you think how long do you think the community would take before it starts becoming a household name?
Well, it all depends on the community and the adoption of the technology. We are talking with a number of universities who are looking to use it as the main middleware for doing experimentation, especially with closed-loop feedback control systems. So we're on the cusp of actually proliferating the software in a really big way. So we have no timeline as such. It's open source. So whoever wants to take it and use it, you're more than welcome to. And it would be great if you can share some of your application cases with it as well.
I look forward to kind of having a further deep down read on the articles you said. So it would be lovely to have the links posted in the chat. Are there any other questions for Bhupen? Okay, I assume it was crystal clear for our audience in that case. So thanks, Bhupen, once again for taking the time to present for us.